Hi all, this is Nicolas Zabaras. We're continuing with lecture 3 on some of the fundamentals of probability and statistics as part of our machine learning course. So today we're going to visit some more distributions. So we're going to discuss about the student T distribution, the Laplace distribution. We're going to say a few words about the gamma and beta distributions and the chi-square distribution. And we're also going to introduce the inverse gamma distribution and the Pareto distribution. And then as a sort of preparation for our lecture next Tuesday, I am going to say a few words about covariance, correlation, and independence. So the goals for today's lecture are to familiarize ourselves with a few more distributions, to understand from where they come, in particularly students T, and see some of the properties that can be handy later on when we start discussing about Bayesian inference. And next, we're going to introduce the basic concepts of covariance and correlation, and we need to recognize the differences of two variables being uncorrelated versus being independent. And of course, we will discuss more of this in the follow-up lectures, but today we will get a first idea of what that means. Okay, the references are the same as in our earlier lectures. So in many ways, I'm relying heavily on Bishop's chapter 2. This is an excellent reading for those with a machine learning perspective, so that's my reference to be recommended here. All right, so let's go directly to the student T distribution. The student T distribution takes this rather complicated expression. So, we have lots of gamma functions, and all of these terms on the front are being used to normalize this distribution. You can anticipate from the terminology that mu will be the mean of the student T distribution. Now you may think that lambda is the precision, and actually we will see that in general lambda is not the precision of the student T distribution, and nu is what is called the degrees of freedom of the distribution. So you may see in books lambda being called the precision, but I can tell you before we prove it that it actually turns out to be the precision of the student T distribution only on the limit when the degrees of freedom go to infinity. So nu is the degrees of freedom again, and even though we have not seen the Cauchy distribution, I can tell you when the degrees of freedom are equal to 1, the student T distribution becomes the Cauchy distribution. And a more important property that we will actually sort of highlight how we derive this is that as nu going to infinity, the student T distribution becomes a Gaussian distribution with mean mu and precision lambda, and so you can extrapolate why people call lambda in the student T distribution precision, because at least asymptotically it does become the precision of the Gaussian where this distribution converges to. Okay, so let me just highlight, and again we're not going to spend time with derivations and proofs, but let me just highlight why when nu going to infinity this distribution becomes a Gaussian. So what I'm going to do is I'm going to write this power here. I'm going to write it equivalently as the exponential of minus. I'm going to bring this whole exponent down here. So minus nu plus 1 over 2 log of the bracket term. All right. You can see if you put this inside, if you put this in the power of the log, and then you have exponential and log will cancel, and you get the left-hand side. So the student T distribution is proportional to this exponential, and if nu is very big, I can use an asymptotic expression for log of 1 plus a small number, And the first leading term when you do a Taylor series expansion is that small number. So I can approximate this log as follows. So I can approximate this log as this term here plus some some lower order terms, all right, that they are negligible. So the leading term is a quadratic, and you can see immediately if you put things together and you take nu to go into infinity, so nu plus 1 over nu converges to 1, basically becomes 1. So you get the exponential that you're familiar with, the Gaussian, the univariate Gaussian distribution. So the student T distribution as nu going to infinity does become the Gaussian distribution, and as a matter of fact, it becomes a normalized Gaussian distribution. So the normalization, it's something you don't have to worry as nu going to infinity, and the reason is that this distribution, as you see it here, is normalized for any nu, so obviously it will be normalized as nu going to infinity. So let me show you a few plots of the student T distribution. So here you can see the student T distribution for different values of the degrees of freedom nu, going from very small to very big, and you can see as nu becomes bigger and bigger, this distribution becomes more Gaussian, and you can see the more Gaussian nature from the fact that the tails actually, this curve here converges way faster as x goes to minus infinity or plus infinity, when the other distributions, the student T distributions, you notice have much heavier tails asymptotically. So actually we can say, and I will emphasize this again, the major difference of the student T distribution from the Gaussian is the presence of heavy tails. Now, some formulas, the mean I mentioned before is mu, but caution here, the mean is only defined when the degrees of freedom are greater than 1. The mode is equal to mu, and the variance is given by this nice expression and only defined if the degrees of freedom are greater than 2. Now, again, you may ask, what does it mean that the mean is defined only when the degrees of freedom is greater than 1? Means if nu is less than 1, when you try to compute the mean, actually the integral calculation that you need to do doesn't exist. And effectively, it is the heavy tails that result in this type of outcome. So in our case, the mean is mu if the degrees of freedom are greater than 1. Okay, now let me just plot this student T distribution and trying to compare it with the univariate Gaussian. This is this black dotted curve, and also the Laplace distribution that we will see in a slide or two. So the three distributions sort of look the same, but when you pay close attention, you can again see that the student T distribution has heavy tails, all right, has heavy tails, and also you can see that the Laplace distribution has more probability mass around x equal to 0, and the plot on the bottom provides the same distributions but in a log plot. So these are the logs of the three distributions. So I already mentioned that the mean and the variance of the student T distribution is undefined when nu equal to 1. And what I want you to pay attention is looking at the log plot of the student T distribution. You notice that in this regime you have one curvature, and in that regime you have another curvature. So in conclusion, the student T distribution is not log concave, and I know some may start wondering who cares and why is this important, and the only thing I'm going to say right now is remember the way we define the parameters of distributions before. We maximize the likelihood or the log likelihood if you like, or equivalently minimize minus the log likelihood. So if it happens that minus the log likelihood not to be a convex function, there are no guarantees basically for a global optimum in that optimization problem. So there may be other things that we have to worry. And you can see certainly the student T distribution is not convex, is not concave. So that's something that we may have to account in our calculations later on in the course. Okay. I mentioned that when nu equal to 1, the distribution becomes the Cauchy distribution. Actually, you can take this as also as a definition of the Cauchy distribution. And I already mentioned that for nu equal to 1, so for the Cauchy distribution, due to the heavy tails, the mean doesn't converge. Okay. In practical applications later on, when we're going to use the student T distribution as a prior for the precision, I'm sorry, when we're going to use the student T distribution, I'm not going to say for what prior, but when we're going to use the student T distribution in our Bayesian analysis, it is recommended to use as degrees of freedom nu equal to 4. Okay, so that's a typical value that you will see in lots of our examples. All right, so you remember the student T distribution had this weird expression, and obviously somebody may ask, how did people come up with a distribution that looks so weird that we claim that has significant relevance in many applications in statistics? Well, a good way to see where the student T distribution comes from is to look in the equation that you see on the top of the slide. So let me discuss a little bit what these equations all mean about. So what we have is we have a Gaussian that has a precision tau. All right, so we have a Gaussian that has a precision tau. And what we do is we are averaging these Gaussians with all possible precisions tau that follow a gamma distribution. And I know I have not introduced what a gamma distribution is, so here in blue on the second equation, I give you the definition of the gamma distribution for the precision tau of the Gaussian. Tau, of course, is positive here, so the gamma distribution is defined from 0 to infinity, okay? So this equation here, what it is think of it as a mixture of Gaussians over a continuum spectrum of precisions, right? So you average all of these Gaussians for all of these precisions, but for precisions that are sampled from a gamma distribution. So you can guess where this calculation is going to go. So this calculation is going to go to the fact that if you average these Gaussians for all possible precisions, you're actually going to get a student T distribution coming out of this. Now, I am not going to bother to do the derivation in fine details, right? But all of these outcomes that we discussed earlier about heavy tails, and also I will show you in a few slides that the student T distribution is way more robust than the Gaussian to outliers. So all of these outcomes have to do with the fact that we are averaging all of these Gaussians. That's how we produce a distribution with heavy tails and a distribution that is robust to outliers. All right, so how do you do this calculation? Basically, we have to compute this integral, and the derivation is actually a half a line sort of calculation that I'm not going to discuss in detail. There is a change of variables. You go from tau to a new variable z, where you call this bracket capital A, and then effectively you have to calculate an integral that you see on the bottom, that is an integral in the z variable. And if you actually recall the gamma function, you can calculate this integral directly in terms of the gamma function. So I remind you the gamma function looks like this. So immediately you can see that this corresponds to a gamma function. So if this is gamma of alpha, all right, so this integral has to be gamma of alpha plus 1/2. So if I put all of this together, I get the distribution that looks like this. That's a student T distribution. It's a little bit different from what we had before in the parameterization, but you can get exactly the previous form if you change parameters. If you defined alpha to be nu over 2 and you define lambda to be a over b, then immediately you get the distribution we saw in a few slides back as our definition of the student T distribution. So in conclusion, always think of the student T distribution being a weighted average, if you like, of Gaussians for precisions that are coming or sampled from a gamma distribution. Okay, and so that's the practical significance of the student T distribution. This is how it is being derived. So let me show you now a little bit about the robustness of the student T distribution that I mentioned before. So what I'm going to do is I'm going to take a Gaussian and a student T distribution and a bunch of data that you see here with our histogram. So when all the data look nice, right, both the Gaussian distribution and the student T distribution, they look very close to each other. Of course, you know, the student T distribution that you see here has heavier tails than the Gaussian, but somehow both of them do a very good fitting to the data set. If now you take an outlier, right, and this is an outlier, obviously this is the wrong data. So if you take an outlier and you try to do maximum likelihood estimation, you try to fit now a Gaussian and a student T distribution, you can see that the Gaussian now is being extended in a way that can interpret the observation of this data point here, but somehow the student T distribution is robust and it changes very little. You know, it does little effort to basically adjust to this outlier. So this is what we call robustness to outliers. And these type of distributions like the student T that have heavy tails are robust to outliers, and this has significant, of course, applications as we will see. All right, so this is basically the same plot. It also shows the the robustness of the Laplace distribution. These plots are being done using the MATLAB 2 box from Kevin Murphy's book. So basically they give you the same message as the earlier slides. Okay, since I mentioned the Laplace distribution, so it will make sense to actually formally have one slide that introduces the Laplace distribution. So here it is. The only thing I want you to remember is that in the exponential you have the absolute value, and I remind you that in the Gaussian distribution we had the square, right? We had e to the minus x minus mu square, and maybe that can give you an idea why the Laplace approximation is also robust to outliers, because in some ways the Gaussian distribution penalizes, when it tries to minimize, it tries to match the data. In the Gaussian distribution you have x minus mu square, so if you have an outlier, the error basically is going to increase by this square power, but in the Laplace distribution the error is only defined by this absolute value, and that is what it adds robustness to outliers when we use the Laplace distribution. A few things about the mean and the variance and the mode. Here are the values directly cut and paste from Wikipedia. And something else I wanted to mention for the exponential distribution, it puts a a lot of its density around x equal to 0 in a way more than what the Gaussian does. In one of the earlier pictures, I make a point of that there is more probability mass for the Laplace distribution than for the Gaussian or even the student T. And this is a very important property, because if you use the Laplace distribution, let's say for prior of the weights in a neural network with millions of parameters, this Laplace distribution, effectively what is going to come is going to introduce sparsity in the model, is going to force many of the parameters to be concentrated around this 0 value where most of the probability mass is, and as a result a lot of these parameters will become insignificant. This is what we mean here when we say this type of distribution encourages sparsity in a model. And as we will see, sparsity and exploring sparsity is a very key ingredient of successful machine learning algorithms. Okay, let me continue with some simpler distributions. So this is the beta distribution. I want you to remember the form of this: x to alpha minus 1, 1 minus x to beta minus 1. This is the beta function that you see here defined in terms of the gamma function. Remember that the beta distribution is defined for x between 0 and 1. This is very important, all right? And both parameters are positive. Now, you can see here a few plots of the beta distribution, and for most values of alpha and beta, you can see the distribution is unimodal. It has only one mode. But if alpha and beta are less than 1, you can see that the distribution basically, so in this case, this blue curve, you can see now that we have two peaks concentrated near x equals 0 and near x equal to 1. Okay, so the distribution, most probably when you use it in practice, it will have one mode, but keep in mind if somehow you use values of a and b that they're less than 1, you may get this extreme situation of two modes. Okay, so here is the expectation, the mode, the variance, and you can visit the Wikipedia site for the beta distribution, and you can see more details. Now, you notice in the definition of the beta distribution, the normalizing factors involve the gamma functions. And again, someone can ask, and say, I have not seen any of these things. Where are these gamma functions come from when you normalize this distribution? Because effectively, if you take the integral of this from 0 to 1, it has to come equal to 1. This is what normalization means. So let me tell you a little bit about what this plot, before I show you what the gamma function is. So this plot shows what I mentioned earlier. It's basically the same plot, right? I forgot to mention that, when a and b equal to 1, right, from the form of the distribution, obviously you get the uniform distribution. So actually the beta distribution can become an uninformed prior, as we will see by selecting alpha and beta equal to 1. And then for alpha and beta less than 1, you can get these two modes near x equals 0 and near x equal to 1. All right, and I think we discussed most of this, and these are a little bit different plots from PMTK, I believe, showing basically the distribution for different type of parameters. Okay, so before I highlight sort of how the normalization of the beta distribution comes from and where these two terms came from, let me just remind you what the gamma function is. I introduced the gamma function in an earlier slide, but let me just give you the formal definition here. The gamma function is this integral that you see from 0 to infinity of u to the power x minus 1 e to the minus u du. And If it happens that x is an integer, this calculation, if you do integration actually by parts, before I even say anything about x being an integer, if you integrate this by parts, you can show that gamma at x plus 1 is x times gamma of x, and if x is an integer, you can actually show recursively, right? You can that gamma of n is n minus 1 factorial. And maybe this is what you remember from other courses, but remember the gamma function can be extended to real numbers as well, not just to integers, but for the case where x becomes an integer, gamma of n is n minus 1 factorial. This comes directly from this relation if you use it recursively. Okay, so let me highlight why this distribution, the way it is written with this nice term on the front, why is it normalized? So effectively what I will need to do for normalization, I'm going to need to prove the equation that you see here. I'm going to need to prove that if I take this integral and multiply by gamma calculated at alpha plus beta, this is the gamma function at a times the gamma function at beta. I am not going to go in the details of the derivation. I want to highlight what is on this slide that you need to do to actually do the derivation. So let me just highlight it, okay? So the derivation is going to start with the left-hand side. So I'm going to take gamma of alpha and gamma of beta. I'm going to write the definitions of these two gamma functions. And I have two integrals, right, in x and another integral in y, and I am going to mix this integration in x and y for x and y going from 0 to infinity, and I'm going to do three different sort of steps to allow me to go from the left-hand side to the right-hand side of this equation at the top. So the first thing you can see here, I have to integrate x from 0 to infinity, and I have to integrate y from 0 to infinity. So the first step I'm going to do is I am going to change a variable y, and I'm going to substitute it with a new variable t. So if y is integrated from 0 to infinity, obviously t is going to be integrated from x to infinity, okay? And this is what you see here, all right? So you can see the integration in x going from x to infinity and the integration in x going from 0 to infinity. So effectively, if you actually think about it, this sort of double integral, it requires that you to integrate over all of this domain, all of this triangular going to infinity. The way the integration is implied here is for a given x, you have to integrate on a little strip from x to infinity, from the diagonal all the way to infinity. So what I'm going to do is, if I have to calculate this area by summing all of these strips from starting from the diagonal all the way going to infinity, from x to infinity, I can actually reverse the integration and select a given t, and then integrate on little horizontal strips that go from x equal to 0 to x equal to t. And this is what I have done in this calculation here. All right, this is my second step as I indicate here. And the last step is actually trivial. You change the integration from x to an integration over a new variable mu, such that x equal t times mu. And when you do that, you actually immediately you get one integral that gives you the gamma function at alpha plus beta by the definition of the gamma function, and another that gives you basically this integral. So effectively we have proved that the beta distribution is properly normalized because if I can go back, right, you can see my beta distribution looks like this, and what I prove is that this integral from 0 to infinity times this normalization factor is equal to 1. Okay, So you can read more and play with the integrals. And again, in the context of this course, it is the derivation is not really much relevant, but I want you sort of not to start thinking that everything we do comes from nowhere, all right? Everything comes with a little bit of calculation, a little bit of effort, and you can see here how the gamma distribution comes to be normalized. Okay, so let me, I'm sorry, this is the beta distribution, right? How the beta distribution written with these gamma functions as normalization factors, how that beta distribution has been normalized. Okay, so let me introduce now the gamma distribution, all right? So before we had the gamma function, and you can see still here the gamma function, but now I want to introduce the gamma distribution. It is defined from x from 0 to infinity, which actually makes sense if you think about it, because you remember when we defined the student T distribution, we took the precision to come from a gamma distribution, so the precision is positive or 0, right? So this is what we have in defining the gamma distribution. So now we have x to alpha minus 1, e to the minus beta x. A is called a SA parameter, and beta is called a rate parameter. If you check Wikipedia, it provides two different parameterizations of this distribution, and actually instead of using this rate parameter beta, it uses beta as 1 over theta, and it refers to theta as the scale parameter. Okay? You can see if you put beta 1 over theta, so you have minus x divided by theta, so theta is a scale parameter, but when you look at beta alone, you define it, you call it a rate parameter. All right, so let me give you some values for the mean, the variance, and the mode of this distribution. Again, I don't necessarily expect you to remember. You can find all of this in seconds looking at these slides or looking at on the web at Wikipedia, and there you will also find many other properties of the gamma distribution and its relation with many other distributions. So please do visit often when you need to do calculations with distributions. So a few plots. This is how the gamma distribution looks like. You get different type of situations depending on the values of alpha and beta. So when alpha is less than 1, the mode is at 0, and as you increase this rate parameter beta, the distribution actually squeezes to the left, okay, and it goes upwards. All right, I'm not showing this in this figure, but you can run this plot demo if you like, and you can put increasing rates beta, and you will see exactly what happens. The distribution basically moves leftwards and upwards as beta increases. Okay, and here is, you know, another plot of realistic data corresponding to some rainfall data. This is a typical example coming from textbooks that is using the gamma distribution to fit this data. Okay, just a few words about the exponential distribution. Has this nice form. It's defined from 0 to infinity. It models effectively the times between events that follow a Poisson process. And for those who maybe remember from their probability course, the Poisson process models events that happen continuously at a constant rate lambda. And I'm actually potentially going to say a few more things about these Poisson processes in 1 or 2 lectures if we have time, but here are some statistics, the sum of the moments for the exponential distribution. One other distribution that is actually not new is the chi-squared distribution that you see here, and you can notice has only one parameter nu, okay, and it is, I mentioned it's not a new distribution because really it is a gamma distribution with parameters nu over 2 and beta equal to 1/2, okay, and you can see the chi-squared distribution explicitly written on this equation. I mean, I inserted it here because we're going to use it later on for when we do inference for the the Gaussian distribution for computing the mean and the variance and the precision. We will in one of the cases we're going to use the chi-squared distribution, so it is good to remember that it is nothing but gamma with particular values of parameters. Actually, let me give you some facts, and there are thousands of those facts that you can find in books. You can take courses on this, but here's an interesting fact. In the case that this nu is an integer, okay? So, I introduce here the distribution from the gamma distribution with parameter nu over 2 and 1/2. So if nu happens to be an integer, you can solve the following amazing result, that if you take little nu standard Gaussian random variables, and you form this summation of their squares, then this sum actually follows a chi-squared distribution. Obviously, this has lots of implications on potentially how you're going to use the chi-squared distribution, but right now, accept this as another amazing result that somehow makes the Gaussian distribution relevant to everything, because now we can see the relation of the Gaussian distribution with the gamma distribution, in particularly this chi-squared distribution that you see here. Okay, since we defined the gamma distribution, I am going to tell you that there is an inverse gamma distribution. So if x follows a gamma distribution, 1 over x follows an inverse gamma distribution with the same parameters a and b. And I give you here the definition of the inverse gamma distribution. The only thing I need you to pay attention, don't derive the inverse gamma distribution by going to the gamma distribution and putting x equal 1 over x, because that is not going to give you the inverse gamma distribution. We're going to learn, I believe in the next lecture or 2 lectures from now, on that probability densities do not transform, when you change variables, do not transform the same way as functions, all right? So there is a little bit of thought that we have to put on how, when we change variables, we compute PDFs for the new variables. So the new variable in this case is the variable 1 over x, right? Let's call this y, 1 over x. So if x is gamma, then y, 1 over x, follows an inverse gamma distribution, okay? And maybe the notation here is, can be under question. It would have been better if I have written down y following an inverse gamma distribution of y given a and b, where y is equal to 1 over x, okay? So that would be a little bit more clear calculation. But the inverse gamma distribution that you see, this is the proper definition, okay? That is given on this second equation. So the parameter a for the inverse gamma is called the say parameter, and the b is called the scale parameter, right? And if you want sort of some intuition why beta is here called the scale parameter, I can tell you that if x follows an inverse gamma distribution, all right, you can actually show that x over beta, if I call that variable y, then that y follows an inverse gamma distribution with parameters alpha and 1, okay? So you can see here x over beta, obviously beta takes the form of a scale for x, all right, since y now follows this inverse gamma distribution with parameters alpha and 1, okay? So beta has disappeared here and has come here in the definition of y. We will say a little bit more about the inverse gamma distribution later on, and actually I'm going to derive the inverse gamma distribution following the definition of the gamma distribution. And again, please don't get confused here. I said if x follows a gamma, 1 over x follows an inverse gamma. It would have been better if I had written here if y 1 over x follows an inverse gamma and I put a y there. And maybe here I should have put also inverse gamma of y and put y everywhere, okay? Because I don't want you to confuse the x that comes in the gamma distribution with this new variable x that follows an inverse gamma distribution. Okay, and here is some of the moments, the mean, the mode, and the variance. And again, you don't need to remember any of this. If you need to use this in your calculations, you just look at the a typical at the Wikipedia or a textbook, and you will get all these answers ready to go. Okay, let me give you the last distribution for this lecture. This is the Pareto distribution. Has this interesting form. Has two parameters k and m. This is the indicator function. So this distribution is defined for x greater than or equal to m. So this density only assigns probability when x is greater than m. But how much greater than mx is defined by this coefficient k. And where do we use this weird looking Pareto distribution? We're actually using it in situations where the things we want to model are not evenly distributed. And a typical example where things are not evenly distributed are things like the wealth in a population, because as you know, very few people are rich and most people are very poor, or as they say, 1% of the population holds 99% of the world's wealth. But also we're using this a lot in natural language processing when we try to model the frequency of words. And words don't come uniformly. There are some words that come more often than others, so they have a higher frequency. And so, for example, the most frequent word takes place twice as often as the second most frequent word, and 3 times more often as the third most frequent word, etc. So those type of situations where we have where we don't have evenly distributed variables or values are modeled using the Pareto distribution. So if you take the log of the Pareto distribution, you get what is called the Zipf's law, that effectively you can see if you take logs, you get in a log scale, you get a linear plot. And here are some schematics of the Pareto distribution for different values of m and k. And I think I forgot to mention, and maybe this turned out to be important, when this k in the distribution goes to infinity, then this distribution becomes a delta function that is centered around this value m. Okay, so that's a useful property to remember for the Pareto distribution. Okay, so we're practically done, and in preparation for the lecture next week, I wanted to say a few words for covariance, correlation, and independence, and this is a topic we're going to discuss in detail in our following lecture. So let me first define the joint distribution of two random variables. So So I'm going to take two random variables that map the sample space to the real line. All right. So these are scalar real random variables, and we're going to define the distribution that x belongs in A and y belongs in B as the probability of the events that through x are mapped to A and through y are mapped to B. This is what this second term here indicates. And I am going to set this probability distribution with this integral over the domain of A and B by using what's called the joint density of x and y. All right, so we saw earlier the density of for one random variable. Now we can see the joint density defined basically by the joint probability of events that we have seen from lecture 1, and I take this as the definition of P of x and y. Okay, we're going to say that two random variables are independent if the PDF of x and y is the product of the marginals of x and the marginal of y. So we're actually going to come back to this definition of the marginals, but you can think of P of x being this joint PDF where I sum for all possible values of y, and the same thing for P of y. But for now, interpret this equation the same way that we interpreted the independence between events, where we use probabilities, but now you notice we use probability densities. All right. So obviously, if you want to formally prove this equation with a little bit of algebra, you're going to have to take the independence of events, use this definition that you see on the top here, and somehow from that definition, from the independence of events, prove that the joint density of x and y is P of x times P of y. I repeat again, these densities don't give you probabilities, right? If you want probabilities, you're going to have to do this sort of integration over part of the domain. But independence of x and y leads to this equation, and we will take it now as is. Okay, so the covariance of x and y, we're going to define it as this expectation that you see here. And if you actually expand this expectation, you can see immediately that the covariance of x and y is the expectation of x times y minus the expectation of x times the expectation of y. And maybe you can immediately see that if x and y are independent random variables, so if this joint density can be written like that, when you use the definition of the expectation of x times y, because this joint density factorizes like this calculation for this term will give you e of x times c of y, and it will cancel with that. So effectively, if two random variables are independent, their covariance is 0. Unfortunately, things don't work the other way around. So if the covariance is 0, so if these random variables are uncorrelated, as we say, it does not imply independence of the random variables x and y. The idea here is that this statement of independence is a very strong statement because it involves probability density, but the statement on correlation involves expectation, so it's a much weaker statement. All right, let me just finish with a few more definitions. So we define the covariance. Often we use a normalized covariance between x and y by dividing by the standard deviation of x and y. I remind you what those standard deviations are. And often when somebody gives you data, the first thing you do is you normalize this data by removing the mean for each random variable and dividing by the standard deviation. So it's normal to, as a first step in your calculations, to define, instead of using x and y, to define these new normalized random variables. And immediately you can appreciate why somehow you want to do normalization of the data like that. The reason, of course, has to do with the fact that now the expectation of this curly x and curly y is equal to 0, and also the variance of both these new x and y variables is equal to 1. Now, this normalization doesn't say yet anything about the covariance or the correlation coefficient, okay? But somehow think of this as each random variable being normalized on its own separately, okay? So we normalize x on its own and we normalize y on its own. Okay, so we are going to finish here with this lecture, and we will continue in 2 days with more fundamental elements of probability theory that are going to be useful as we start doing Bayesian calculations and different tasks in machine learning. See you next time. Bye.